right side is the picture of superconductors, and the part that I highlighted is the one that shows the current that's above zero. Here, like one, it is the voltage. The fact that you don't have any voltage implies that you don't have any resistance. And this is the beautiful thing with superconductors. You don't have this kind of problematic, we can call it property. And when you get rid of that, you can have devices that switch much faster and with lower power dissipation than conventional CMOS. But one of the most important and interesting features is that you have wired superconducting interconnects that do not consume as much as their semiconductor counterpart. And on the right side, you can see a graph from back in 2004 or so that even at that time, we knew that the wires in the processor were taking more than 50% of your power budget, and this is not amazing. So that being said, with superconductors, we know that we can fabricate these devices. Unfortunately, the latest news about having them in room temperature and without pressure were not as expected, but still they're useful, right? So that's a true statement. I assume about superconductors and almost everything. And moving forward, like I borrowed this slide from IARPA years old. You can see that the point of comparison is Barack Obama. They're wanting to take in big superconductor and scale it down, fit it in a cryo cooler. And one of the main arguments was, look, if we manage to build in superconductors, it's not only smaller, but potentially can consume much less power. So here I have highlighted this line that I found the most interesting from their DAA. So if you manage to build it, then instead of 8,000 kilowatts, 80 kilowatts. Amazing, right? So this is a pathway to green high performance computing, and we know that HPC is like a big friend with scientific discovery, so that will be amazing. Another reason why this field invites for more exploration is because quantum systems that are emerging and hopefully will become practical in the years to come seem to rely on superconductor electronics that are placed in the 4K environment for their scale. And in particular, like our studies in the architecture community, Gokul has done work in that direction as well. But so you have to take part of the error correction and control and take it from the outside of the cryo cooler or room temperature environment and put it down to the environment, and this will help you eliminate some noises, so you can access latencies or whatever else is important to make this machine scale. Now, this is all great, but this is not as easy as it sounds. And to understand one of the fundamental differences, we have to see how semiconductor devices. So let me take you back to your early undergrad years where you learned some basic of digital electronics and here we have these devices. And the one fundamental thing that we learned in that class is that information is important in steady voltage levels. Have a low level and have a high level. And then we know that as designers, in to express the duration of whatever you see here as a like square wave. And roughly the duration of every level is in the nanosecond. That's all great. So low level is a 0, high level is 1. You do some timing analysis. Timing analysis tells you that there is enough overlap to perform the logic function that you want. And we can build systems like that scale and work. And this is pretty much what Shannon was talking about like 100 years ago. But if you move to superconductor electronics, you have a change. What happens is instead of steady voltage levels, as you can see now, we have tiny pulses. And these tiny pulses are in the level of like 1 picosecond. And we don't have the ability to stretch them. So, of course, having the same obstruction as on the left, like low level 0, high level 1, and you bring it in here, does not help much, right? Nobody believes that you can align picosecond level pulses to perform some kind of computation. And this creates many problems. We will see as you try to trick the system, you may create some trouble in the way that needs a solution. So what I will promise you in reality is that I will use time in a somehow unconventional way to resolve this problem, so your pathway to success with superconductor electronics. Now, before I go any further, I would like to introduce myself and my lab. My name is Tzimpragos. I'm an assistant professor of ACS here at the University of Michigan. I joined last year, and I'm leading the physical computation laboratory. These are the photos of my students that I could find. Unfortunately, none of them is smiling. Like the sub squad. But I will do it next time. I will have better photos. So our area is computer architecture. And many of you, we force you, if you're in the AC to take 370, you say, why do I need computer architecture? It's not the sexiest of topics. However, I consider it a class. And the reason is changing over the years. In the late 80s, we had the theory from Richard Feynman saying that there is a lot of room at the bottom. In 2020, we had the theory that's kind of opposite, saying there is a lot of room at the top. The problem is maybe architecture is not the definition of the bottom, and architecture is not the definition of the top. The good side of the things is that architecture is part of the bottom and top. So one quote that I like is that the art of good business is being a good middleman, and computer architecture is exactly this. And my team, the way it approaches computer architecture is more of a bridge rather than an island. So the way we try to pursue our endeavors is by looking backward, looking forward, up and down. So it's good to have this kind of expertise in the field of computer architecture, but we believe that we should be able to communicate with people doing different things, ranging from applications all the ways to devices and materials. And this line of work has been recognized both by the computing as well as applied physics community, and that's something that we're really happy and fortunate about. Now, going back to computing, we all know that computing takes time. It's an abstraction of physical processes, and every physical process takes some time. And the typical convention is that less time than more time, right? So the way we think about that is that time, performance, is a measure of quality. So we have metrics like response time, execution time, throughput, and so on. And the way that we try to approach time typically is as an optimization problem, with the idea again being sooner the better. Now, if we get out of this domain of traditional computing, however, and we look how people doing real-time embedded systems consider time, then we will figure out that there are papers out there that claim that computing needs time. And what that means is that here time is treated as a functional property. A good example is that, maybe the principle is that less time is in some cases no better than more time. And this is opposing the kind of performance. You can think about like your cars or your ABS. You want it to work, but you don't want it to work faster than it should. You don't want it to work slower than it should. In both cases, it can be dangerous. So in real-time embedded systems, things just have to happen at the right time. Happening faster or happening later is equally bad. That means there's a bug. But we saw that computing takes time, computing needs time. What about computing using time? And what I mean by that is, can we use time as a computational resource? And this is like a question that we had a few years ago, and it came to an observation that the machine learning field was taking two extremes. Like one extreme was that of people believing in analog AI. They were like, analog is the way our brain works. That's what we are going to adopt. We'll pick analog machines and we have brain-like efficiency, boom. Now there is another school of thought, like Tzimpragos or Intel, that said, forget about analog, binary and digital are the king and queen. They're not going anywhere. Let's build more. This is the future. But in this kind of dilemma, we found that there is not a black and white situation. Instead, it's a spectrum. And data representation and style of computing don't have to be one or the other. Maybe we can cook something smarter and have happy medium case. And what is this happy medium case? This is our digital temporal codes. So please pay attention to the next slide, because this is, if there is one key takeaway, maybe this is that. So what we said is that we are going to use a single wire per variable. And what we will do is we will keep a digital abstraction that has a low level and a high level. Now, if this is a representation you have, what we achieve is that we minimize the number of wires that we use, and we minimize the switching activity, because now every wire will switch from low to high just once. If we have this representation, Now we can also go one step further and quantize it in terms of time. So this is a property we buy from synchronous systems. And what we can say is that the information in this kind of representation is encoded in the delay between your reference point on the left and the time that an event or state transition happens on the right. So A starts from a low state and jumps to high state after 2 cycles. This is going to represent our number 2. And if you have B is equal to 5, that means that you start from a low level and you will jump to a high level after 5 cycles. So if this is the case, we're far away from the Boolean interpretation because we don't have zero velocity. That's a multi-value logic. And if you have a multi-value logic, you need multi-value representation, so you need logic that handles kind of representation. Given that we talk about time, we have a polynomial. But this time is not used for propositional purposes as typically the case. So when you go meet your friend, what you care about is who arrived first arrival. In the case of the 2, the first arrival is here the orange signal because it arrives before the green signal. If you have first arrival, you will have last arrival. The last arrival in the particular case will be equal to 5 because the green signal arrives last. Then you will have delay. So you can say, I want to delay signal A, but you need the time before A was arriving at time 2, now it can arrive at time 4. And our last operator is one that we borrowed from neuroscience, it's our bouncer, the inhibit operator. So what happens is, here you can read that as B inhibits A. If B arrives before A, then B will block A propagation. Otherwise, A is going to propagate through the gate without interruption. So here A arrives before B, it passes. If I put the 2 operand, nothing passes through, and this is equivalent to infinity, given that no event will happen. Is it all right? So when you look at this kind of operations, then the next concerning thing is how to be implemented easily. So again, taking back to your digital exam course, you will see that there is a really easy way to implement this function. So you can implement first arrival with the plain OR gate, because the OR gate will fire as soon as one of its inputs is high. While if you want to implement last arrival, you can implement it with an AND gate, because the AND gate requires both signals to be high in order to fire. In a similar way, see that you can implement this delay with some flip-flops, and finally the inhibit with an augmented SR latch. And if we revisit the logic abstraction, what we will see is that this first arrival, last arrival inhibit, under the assumption that shorter delays represent smaller values and longer delays represent larger values, they can be thought of as minimum, maximum, constant addition, and a low-pass filter function. Now, if you have this abstraction, what we did is we took these logic operators and we translated them over functions, like functions over natural numbers. And these functions, we can show you, were functionally over the set of natural numbers infinity. An interesting next step is also to try to connect these kind of functions with some known algebras. And what we did is we made some connection between these 4 operations to tropical and fuzzy algebras. So our goal was not to unlock one application, but to unlock a family of applications. And one application, or one of the first applications that we explored in the context of machine learning in particular, was that of accelerating ensembles of decision trees. Well, given that we called this logic raised logic, we called our trees raised trees, and we built an architecture that looks something like the one on the left. And unfortunately, I don't have time to go through this in detail. But the results that we got were very, very initially surprising, because by making comparison between solutions like Minerva, that's a conventional DNN accelerator from Harvard, and IBM's machines that are neuromorphic, we realized that we have energy delay product gains that are between 3 and 4 orders of magnitude better. Now,
so I mean, I'm not familiar with Minerva. So what exactly were you doing there? Were you training or?
No, this is for inference.
Just inference.
This inference we use like plain MNIST data set at the time was what people using for all these exotic things. And we try to perform like comparisons based on different settings. And again, when you see results that are
sorry, and the ideal is the machine precision.
as you go to the left, what you want makes it one perfect accuracy. And here you have the best energy, the lowest energy delay product, so winner. Yes. Accuracy means the prediction accuracy, like for example, when you try to take forward, it's one. Yes. Yeah, and the reason why we want that is not in training, but we want to be sure that we don't introduce any new noise. People, for example, like the solution that you see now, have better results, right, in terms of energy delay product, but they make huge discounts in terms of accuracy. So what we wanted to demonstrate is that we don't have to make such discounts to achieve good energy delay product. And when you see results that are 3 or 4 orders of magnitude better, you may question why, right? I mean, maybe you made a measurement error. And we thought about that. So we found an explanation. The reason is that we're using a single wire per variable, and these wires switch at most once throughout the round of computation. So you minimize your capacitances potentially and your switching activity. Then you have extremely short critical paths because you're able to use a single inhibited gate. And because your inhibited gates are so tiny, you don't have to do lots of resource sharing, which is one of the main problems both in neuromorphic and conventional design approaches. And as I said earlier on, we don't introduce any new source of inaccuracy. So our process is very deterministic. You don't have degrees of staticity. So this was great, but I promised you to solve the problem of pulses, right? And in the case of the pulses, as I said, it's not easy to translate into 0 and 1. So typically what people from this community are doing is they introduce a third signal, which is a periodic pulse train. And what happens with this pulse train is it defines an interval of interest. So if a data pulse appears during the clock interval, it's understood as 1. If it doesn't appear, it's understood as 0. All good, but if you look at the level of the system, it creates a bunch of problems. And these problems don't let you really scale or don't allow you to have some kind of compatibility with existing tools. And this is one of the main issues why the field has stayed behind. So forget about it. Remove the clock again and see if we can have another solution. So the solution we said is if we cannot have zeros and ones, maybe this temporal paradigm that we introduced before is going to solve the problem because it doesn't require propositions. It doesn't require true or false statements. And here, that's exactly what we did. We started mapping this logic to superconductor electronics. We designed the basic cells in this technology. We figured out how they work. And then we went back and we replicated our decision tree example, but this time with superconductor electronics. Our analog simulations show that we have speeds that can be 4 times faster than CMOS in this technology. And just to make sure that our ideas work well in practice, we collaborated with a folks at MIT Lincoln and we fabricated this design. Now, during this design, one thing that we realized is that the left part, the ones that you see with the eye, is that the swirl also happened and implementation was relatively straightforward, but the decoder was not. And in the effort to build this kind of decoder, what we realized is that there is a duality. In the case of level-based technology, first rival and last rival can be implemented with force and circuit or cells. In the case of a pulse-based technology, like the one we talked here in superconductors, you can do the opposite. You can do the first rival and last rival to implement or and and. There's a little bit more that has to go into this cocktail to make it work, but I can discuss about it offline if anyone needs. The thing to take away is that when you try to see what this means in terms of performance, and here I'm using again energy delay product, and I compare regular SFQs versus our alternating SFQ example, what you can see is that when we start from a system that has about 10 to the 4th logic gates, and this is roughly the complexity of a small void RISC-V processor, you have gains that are 20, 30x. When you play to a system that grows by 10 or 100x, and the gains keep growing. And the reason is now you can adjust the degree of pipelining freely and you can do optimizations that before you were not able to pursue. And these kind of gains are on the pessimistic side because according to the literature, if you revisit the assumptions, you will see that you have good reasons to believe that you will boost it by an order of magnitude further. Now, at this point, I know that I'm reaching the end of my talk. I would like to summarize. The common belief has been that this is the world that we know, and this is the world that we teach you as undergrads. Tell me that we have and or a not. There's a Boolean logic on top of that you can leverage using RTL languages, and then you can use that to build von Neumann or data flow architectures for any application you like. What I hope you got from today is that this is not the whole picture. The whole picture is that you can use the same and or and not as your foundation at the cell level, but you can have a different logic interpretation. And with this different logic interpretation, you can build a different stack. Or you can rebuild your stack. And in the case of watching this as a class, in the case of technologies that don't last, like the one in quantum, this is a necessity. This is no more an option. And just to make sure that you all leave this remembering this kind of little detail, I borrowed a phrase that's quite common to those that live in this country for long enough. So they say, if all you have is a camera, everything looks like a brain or a nail. My brain is in the next slide because I rephrase that. So if all you have is a Boolean logic, then everything looks like and or a not, and this doesn't have to be the case. And the use of time in an unconventional and funny way cannot solve only problems that relate with logic, but also can solve problems that relate to memory. Here in our latest work, we have reinvented rate track memory in the delay line memory. ENIAC machines, like the one we have at the entrance of PBB, based on delay line. Our insight here is that you can use low attenuation superconducting interconnects to achieve much better results. And you can find this work now online. But if you have any questions, I'll be glad to talk about it. Thanks again for your time and your attention.
Very fascinating. Go ahead.
Yeah.
Yeah, I have a question about the temporal logic gates.
Yeah.
So when you show the late arrival, I think it was a slide that had like 2 pulses. How does it actually compute that it was a 1 if the pulses do not happen like at the same time?
Sorry, can you repeat that?
Oh yeah, sure. For example, here you have the late arrival. That would be like kind of an end of the signal.
Yeah.
How can you capture that if the peak in A and B do not happen at the same time?
Oh, here you don't have to. Okay, I'll tell you. First of all, you see that they don't have to happen the same, right? So what we did is, given that you don't have any way to synchronize things, we thought is there is a beautiful field called asynchronous computing and synchronous logic, but it's not, the asynchronous operators are not used for computation or used for interfacing. So what we did is we took the asynchronous operators and we camouflaged them in logic operators. So then we took the join operator or new layer C element, and we said, okay, you know, why do you need it just as join? We can make it an end. So this is how we played it. We borrowed ideas from asynchronous and decorated them a little bit. Yes, please. That's a great question. So the question is about use cases, right? If you try, it's a unary scheme. You keep expanding time in a kind of an exponential way. So if you try to build a processor that has 32 bits, good luck, you'll wait for a while. But this is not the case every time, right? For every application. Machine learning, we've seen that 8 bits are sufficient, and this is what our prior work on CMOS wanted to demonstrate. This time of the year, my group explores applications related to sensors, and we believe that this kind of encoding can simplify a lot the sensor interfacing. So this is what I believe is a killer app for like CMOS temporal computing, and also going to bring it into superconductors for anything else that's emerging. Going to emerge to new technologies, I think that this abstraction is useful because, let's say, CMOS, for good or for bad, has the same abstraction as relays and tubes. Superconductors don't have the same abstractions, but guess what? Optics don't have the same abstraction. Biological systems don't have the same abstraction. So if you want to build computers out of new devices, it's wise to rethink a little bit the full stack rather than trying to turn everything into NOR. So hopefully one day my thought will be famous, but until then, I keep promoting it. Thanks for your time.
So, quick question. So I'm thinking of typical applications in scientific computing, and thinking of you have 2 large vectors and you take a dot product.
With my temporal scheme.
Like you with your temporal scheme.
The question that you say is, I have 2 large vectors, and I want to do,
let's say 2 vectors.
2 vectors,
Yeah.
and I want to make multiply.
Dot product.
Dot product.
Yeah.
Can you do? Yes, you can. Is it gonna be great? Maybe.
So what needs to happen to make that?
I think it is, with superconductors, you don't have to do it like, just make something clear. In superconductors, the same operators can be used to realize the matrix dot product in any way you want. In the control domain, we can do it. It's just the nature of encoding doesn't favor that.
Yeah.
What we try to do is, you may find happy in between now between the two extremes that's binary and only important. So if you
Yeah.
may be able to find something in between that can help improve kind of metric, or what potentially you can do is you can think of algorithms, for example, if you're targeting machine learning, that don't rely on matrix multiply. They don't rely on linear algebra. We have other algebras in the account, mathematical algebra, algebras, fuzzy algebras, other algebras that may be able to achieve the same goal without you trying to do only the same operation. An example is when you try to do clustering, you care about distance, right?
Yeah.
You can calculate distance with L1, L2, or L infinity. As you play between the norms, you can see that all three norms find distance, but they use different fundamental operations. In L infinity, you use min and max. In L1, you use min and max. These two are something great for us. If you want an L2, no matter what, this may be problematic. So there is this kind of trade-off that then maybe you have to sacrifice some accuracy, or maybe you have to rethink your algorithm,
Yeah.
and then you will gain orders of magnitude in terms of energy.
I just get, because you mentioned that, you showed the inference in the neural network, right? Using the.
It's some decision trees, it's ensembles. of
Oh, it's a
decision
decision tree. I see.
Yeah. So it's ensembles of decision trees, and the reason why we pick decision trees is because the nodes
Correct.
are very easy to be mapped, to be integrated, and what correct functions. In neural network now we do things that are a little bit more on the Hebbian style learning.
I think just as the Lohan paper to be written,
Oh yeah,
take advantage of your things for. some of the-
if you want to write a paper, please let me know. Don't write it without me. I will appreciate it. But yeah,
But yeah, thank you very much.
thank you.